So this will be 1245. Question, or part E. So you're given cyclopentene and then a series of 4 chemical reactions. So this is a type of problem where you asked to predict the product, and so it does have 2 of the things that you asked about, an oxidation and a Grignard. So the first thing is something from 255. There shouldn't be too much like reactions from 255 on this exam in terms of like this context, so it should be a little bit more relevant. So the first step is basically the hydration of an alkene to an alcohol. So from that, the H3O plus is giving you this. Secondary alcohol. So say you were just starting with that, and then you had to do 2, 3, and 4. That's where your questions would come in. So you have a secondary alcohol. The carbon bearing the OH group is at an oxidation state of what? So we're at an oxidation state of 1. So this reagent, H2CrO4, is the Jones reagent. So that's an oxidant. A secondary alcohol can only go up 1 oxidation state. So it's going to go up to what functional group then?
It can only go 1, you said? So
It's going up to a ketone. So it can't be an aldehyde, because this and this are both carbon. So if that's oxidized, it's a ketone. So we're getting cyclopentanone. And here we're now at an oxidation state of 2.
with the reagent, can you, if like that was different and it was like an H, could you get an aldehyde? Or with that reagent, you can only get a ketone?
With this here, you can only get a ketone with that.
Yeah, but like if that was changed and you were using that reagent, could you get an aldehyde?
If this substrate was different,
you could.
yeah. So we'll go through this and I'll put up one where you do get an aldehyde so you see the difference. So now you're at an oxidation state of 2 and you're treating with a Grignard reagent. So in a Grignard reagent, this is the thing that's adding, so I highlighted that in blue. Then this thing over here is just the counter ion. So pH stands for phenyl. So what does that look like? So you have a negative benzene. The magnesium bromide is plus. The carbonyl has this polarity. So the negative charge of the benzene is attracted to the positive charge of the carbonyl. So once you form that carbon-carbon bond, it's now a reduction because it's going back to an alcohol. So what classification of alcohol are you forming now? So it's a tertiary alcohol. So that's the Grignard. So the key word there in the mechanism is an addition. It's a nucleophile adding to a pi bond. Then the last step with water is just the protonation, so an acid-base reaction. So you're ending up with a tertiary alcohol. So if you were starting with a primary alcohol and you oxidized it, it would go to an aldehyde. So we're at oxidation state 1.
If you use that one, then wouldn't it become an acid?
Yeah, this one will.
Okay.
It'll do this first, and then it'll go on again. So this is like a 2-stage oxidant. So we're at 2. And then you end up at 3 with the acid. So you can never forget this stuff, because when we get into the next module, like this sequence is important, because the acid is the starting point for every oxidation state 3 derivative.
If you used the PCC or sworn, though, that would just give the aldehyde, right?
Yes.
Okay. On the test, are you gonna, like, if you ask us that, is it gonna be named like PCC, or are you gonna give us the actual structure? Because I only know it by like the name.
I think I think all the exams have like the structures. So I don't think there's a sworn conditions on there,
Okay.
if I recall.
So.
Let me tell you, I told a student today that, you know, the only thing worse than like taking an exam is writing one. By the time I got to question 10, I'm like, what should I do for the next 20 questions? I mean, it's like.
Is it like the test last year where we got like something and then we had like 7 questions about it, or is it individual questions?
No, they're all separate.
They are?
Yeah.
Plus. Okay, I have a question like after this is all done. Just remind me. Someone remind me.
What's the meaning of life? I don't know.
No, it's about like class and stuff. There's other stuff you could be doing right now. I got a question.
Sure. Next up.
I actually still have a question about this. So, like, what does the Grignard addition do? Like, is it just the water, like, that's being added in that step, or?
No, it's this group here. This pH group is that phenol. They're forming a new carbon-carbon bond.
It's always whatever's in front of the MGBR, right? Like if it was an ethyl or an ethyl,
Right.
that's what you would add.
Exactly.
Okay.
So.
And then you just, it becomes an alcohol then.
Right. So the big picture of this, it's hard to appreciate if you're not an organic chemist. So we'll look at in the next module a way in which enzymes in your body make carbon-carbon bonds. So making a carbon-carbon bond is like the hardest thing to do in nature. Your body does it a certain way, like in labs, people have figured out how to do it sort of that way. But like 100 years ago, no one knew. And like this is like one of the first methods on how to do that. And again, the reason we do this is to make sort of molecules, and these things have shapes, and the shapes are what will interact with an enzyme to be like a drug.
So when you form epoxides, which is a big clarification, it's always going to come from an alkene, correct? Or like from what we're talking about?
Yeah, so I can, on the next slide, there's the way I showed you a couple weeks ago, and then there's the way I showed you last semester. So I'll refresh your memory on that. But they do come from alkenes.
Okay.
So let me pick an example out of the book. with epoxide formation. It's the law of unintended consequences. Do you ever hear that? It's like, you don't take this exam, 10 years later you're homeless. And you know what I'm saying? Like, that's the...
That's true. You guys are with us, right, Margaret? For which class? Physics? Yeah, I have some physics. You're not physics?
So this one does involve epoxide formation. And what you're asked to do is transform an alkene into that ketone. And so this, I would say, maybe a bit daunting if you're not used to thinking this way. So if you count the carbons in the starting material, you have how many? And in the product, you have how many? So you have added a carbon. And so maybe what I'll do is I'll just go through in the forward direction, list the reagents, and then show you how I would think about this in the reverse direction. Thinking it through in the forward direction is a lot harder because you don't know how to get that fifth carbon in there. So the first thing you would do is treat with mCPBA. So that transformation is alkene to an epoxide. So maybe what I'll do is put, just sort of number this, 1, 2, 3, 4. If I use that same numbering system in the product, so where I'm drawing the dotted line, that's where I have to make a new bond. And so I'm sort of set up to do that now by treating with a Grignard reagent with this methyl magnesium bromide, because an epoxide is an electrophile. So in this case, we have methyl minus. And again, your counter ion is the magnesium salt. So you have a choice of which carbon that can attack 1 or 2. Since this is an SN2 reaction, maybe what I'll do in blue, I'll classify this carbon as a primary alcohol. The other one is secondary. So there's all sorts of different numbers going on here, and they mean different things, so just be cognizant of that. So the methyl will attack the primary, and then we then break that bond. So actually we have to do 2 more things. You can see that we're now at an oxidation state of 1. So I'll write that in green. In the product, we're at an oxidation state of 2, so we have to do a protonation with water. So that's step 3. And again, that's just a proton transfer to get the neutral alcohol. And then this is where you would use something like PCC, so pyridinium chlorochromate. So that's doing the oxidation of the secondary alcohol to that ketone. So everything I just said in the forward direction is sort of how you would think about it in the reverse direction. Because it's hard to look at this and say, okay, I need mCPBA. So you can sort of think, okay, across these there can be an epoxide. So that's sort of getting you back to something like this. And then you know from the SN2 chemistry that it will open the least substituted. And you had another comment or something about epoxides. Oh yeah, the other way to make. So that reagent mCPBA is a peroxyacid. So it's just something that has 2 oxygens. So the other way of that you could take that alkene from 255 is a 2-stage process with bromine water. So this is called a bromohydrin that you then treat with sodium hydride and THF. So that'll do an acid-base reaction and then the displacement.
So this is like, the one on the top is like what we're expected to do in 256, but like the one on the bottom would have been like how we would have done it in 255.
Yeah.
Okay.
So this reaction delivers this oxygen in a syn stereospecific way. So it's a lot of things. It's basically plunking an oxygen down where you form both those bonds at the same time. This, you're putting in the alcohol oxygen with the most substituted carbon, the leaving group at the least. That deprotonates that and attacks and leaves. So the mechanism by which that happens is sort of different.
Can we do like an amine question too? I know that's like so general, like something about whatever you think is gonna be on the exam.
So in this problem, they're asking you to, how would you carry out the following transformations?
Does that say ME, the CO2 is an ME?
Yeah. So it says there's 2 steps that you need to carry out to accomplish this. So you have an amine, and that's a secondary amine. You have a chloride, that's a primary chloride. The secondary amine is becoming a tertiary amine. And the chloride is becoming an azide. So both of these are SN2 reactions. So it doesn't matter which order you do them. So to get the azide in there, you would treat with, say, sodium azide. And maybe use acetone as the solvent. The second step, you might treat with a base, say sodium hydride first, and then you need a methyl group, so then methyl iodide. So that the base, sodium hydride, just simply deprotonates that, so you get the N minus, and then you attack the methyl iodide. So again, part of maybe helping yourself on these exams is writing stuff. And I know a lot of students don't write stuff, because when I looked at like your finals, that piece of scrap paper, I think there may be like 5 people that actually like filled out like the whole front of one of those sheets. And to me, that's sort of, I don't know, I can't keep that many things in my head to consider. So if you write these things out, I think it'll help you quite a bit, because just recognizing the change is important.
For number 2, could you also use like NaNH3? Or no?
Say it again.
Like for number 2, instead of using sodium hydride, could you have used Na and then NH3? Like NH3 is the.
No, it would be NaNH2.
Is that what I meant? That is what I meant, yeah.
So yeah, that's sodium amide.
Okay.
So that's the conjugate base of ammonia. So maybe we can do another one in terms of basicity, and this would be 2236. We'll just do B. So we have 2 nitrogen-containing compounds that are in different functional groups, and it's asking you which of the following is the stronger base. Remember what, I feel like I repeat myself ad nauseum when I say this. A base is something that abstracts a proton. The thing abstracting is the lone pair. So we have pyridine and dimethylacetamide. So which one do you think will be the better base? The ace of base, as it were. The pyridine is. So what's important to recognize is, like, this is the letter N, and that's 2 dots, and it's the same thing this lone pair resides in an sp2 hybridized orbital. This lone pair resides in a p orbital due to resonance. So that resonance form looks like this. So because that lone pair is pushed up onto the oxygen, it's less available to abstract a proton. So pyridine wins the chicken dinner.
This might be like a dumb question, but I know you said like resonance has to do with like the system. Like, so why couldn't that like lone pair on pyridine do it with the one double bond?
So that's what's deceptive about this, because when it's conveyed this way, it looks the same, but it's not. So what does it really mean? So that nitrogen is sp2 hybridized, and so are all the other carbons. So if I'll just take a sort of a minute to draw this out in a different way. So I need to take up some space here. So instead of drawing the line as a double bond, I'm actually going to put the p orbitals in. So we have a p orbital on nitrogen, and then this adjacent carbon. So then we have the next set. And then the last set. So those are the p orbitals that make up those double bonds. This lone pair is not in the pi system. So this is an sp2 hybrid bond, so is that. The lone pair is in the third one, the third sp2 hybridized bond. So I'm just going to draw that sort of coming out. So you see in the dimethylacetamide, you have 1, 2, 3, and those are sp2 hybridized bonds. So this nitrogen is not sp3 hybridized. The lone pair is then in a p orbital, because these are two p orbitals that form that. So you get this resonance form. That's how it delocalizes. So I think that's probably a concept that a lot of students don't pick up on. And it's important if you do go into biochemistry that this is super important, because peptides are made of amides, and so proteins are polypeptides. And so when those things resonate like that, it affects the conformation. And so even though this is like the primary structure, say you have 1,000 of these things lined up, it coils in a certain way, and that the way that shape is what gives it its reactivity.
You're not talking about the bubble, like the blue thing?
Like when we were talking about resonance and stuff, that was like associated with the 3-atom system.
Yes.
I know, you put up like the structure like saw like the purity and I was like, how does it not have resonance? Because I was like it does have, and I was so confused.
So it doesn't have resonance because of the p orbitals?
This lone pair does not. These pi bonds, they have resonance, but this
Okay.
lone pair here does not.
That makes more sense now.
Yeah,
I
I
didn't-
was like, I'm still not
And
figuring it out.
because it's not in, the lone pair is not in a p orbital, it's able to work as a base, and that's what gives it
Right.
basicity. Okay. Alright.
Next topic.
So, I don't know if I was confused on the retrosynthetic analysis and organometallic synthesis and acid-base chemistry, just because like, I don't remember if we went fast that day and I just got lost somewhere or what, but like, is that just with, what did we do, like, aldehydes and ketones and like all that stuff that we did before?
I mean, it's just a way of thinking. So, like if you're, we'll do a problem, but if you're given a final product, like you have to design a way to get there. So retrosynthesis is thinking backwards from that to something you can buy. So there's a big, I don't know if you watched the State of the Union, but Trump said he's going to hit the pharmaceutical companies hard, make them reduce their costs for prescription drugs. So I don't necessarily agree with that because it takes a lot of money to make a drug come to market. I mean, you can't go to that tree out there and just like shave the bark off. You know what I mean? It's like a lot. It's like the cost to make a drug is like $2.7 billion. So they have to charge on the back end to recoup that, right? And so a lot of these drugs, you know, say it's like a 15-step synthesis, like 15 steps, and you have to make like metric tons. You know what I mean? A metric ton is like those tankers like you see on a train, like those big things that haul like petroleum. I mean, that's what they're using to make these things. So it costs a lot of money. And so retrosynthesis, you're looking at a way to do that the most efficient, right? Because the more steps, the more time, the more patients die. And obviously you don't want that because then they can't buy your product, right? So we'll look at a problem in here and how to make alcohols. So you're like thinking backwards from the alcohol oxidation state to something a little bit simpler. So I think we did we did one of these in class, but this would be 1236B. And they're giving you the following. So you have that molecule, and it's asking you specifically which aldehyde or ketone you could make that from, but then we'll sort of dig a little bit deeper and look at how we can make it using Grignard reagents. So if I put in this H here, and what the question is asking you is what aldehyde or ketone would that come from if you were doing a reduction? So looking at that, would that come from an aldehyde or a ketone? It has to come from a ketone. So here's the oxidation state 1. So when you're thinking backwards, in retrosynthesis, you're doing an oxidation, because the forward reaction is what you would actually carry out in lab. So a reduction with like sodium borohydride is adding this substituent. So it would be the ketone.
Okay, so it's a ketone because you have carbons on both sides and you're adding that hydrogen.
Yes.
Okay, so that hydrogen wasn't already there.
Right, so this is the retrosynthesis. And so the reagent that you would be adding is the H minus of the hydride. So in the forward direction, you would use like sodium borohydride. So that's one of 3 ways of making that. So we can look at 2 other ways in which you would use basically, if it's hydrogen, you'd come from like a hydride source. If it's carbon, it comes from a Grignard. So you're,
Can you do that one more time?
So when we thought backwards this way, because we're adding H, the H's will come from one of these reagents. So we made that bond. If we want to make a carbon-carbon bond, either this one or that one, that's when they're coming from a Grignard reagent. So we have 2 other ways of doing this. So I'll just call them the 2 pairs here. The Grignard and the carbonyl. So if I want to split this bond right here for pair 1, this is the carbon that's oxidized, right? It's at 1. So it's going to be the carbonyl. And here it's going to be at oxidation state 2. So it's going to be what sort of functional group? It's going to be an aldehyde. And this is going to be the Grignard reagent, so the negative charge is going to be there. So if this adds to that, that gets reduced down to the oxidation state of 1, and then you're making this bond. So that's the way of thinking backwards about it.
So, in order to determine like each step, do we just like pick one of the places to cut or whatever, but like in order to draw them?
Yeah, so
Okay.
basically anytime you see an alcohol, it doesn't matter what alcohol it is, you can do it 3 ways.
Okay.
So this just happens to be Grignard, hydride, Grignard. So the other way, if we cut the other side, so we have a 3-carbon Grignard, and then the carbonyl is coming from this aldehyde. that's the one that starts. These are both aldehydes. That one's a ketone.
And so like for the exam tomorrow, like this could be like a question you ask, is like, how would you?
Somewhat, yeah.
Somewhat, yeah, okay.
So yeah, I'm running an experiment on the exam tomorrow. So we'll see how it goes.
What kind of experiment?
It's a psychological experiment.
So I mean, I'm gonna leave crying.
Hopefully not. Like I said, the questions are not connected, so the experiment is
Will it work out?
will students perform better on that? I think in some sense they're more straightforward.
So we're experimenting with our grades.
So life's an experiment. Think of it that way.
You said it's 30 questions?
30 questions. At some point, it's like, I don't know, it's a bit much. So it has to be, if I make it 10 questions, then they're all worth, what, 10 points? And that's like, then you're screwed if you miss one, right? So the reason I upped it is because the feedback I got from last semester about like the final was weighted a lot more. So you can go into the final with a trajectory that will give you an A, but some students, I mean, will literally fail that final and it'll knock them back to like a C. So all the exams are now worth 120 points. So hopefully that way the final doesn't impact your overall grade as much.
So when we get the percentage, we need to calculate that into like let's say you make like a 70 on it, at 70 out of 100, then we need to calculate that, the points for 120?
So I find percentages confusing, so like what you're saying like confuses me.
Okay.
So that's why I make the class out of like points.
Mhm.
So you're going for a certain point accumulation. Granted, like the letter grade is sort of resolved by a percentage, so 90% of the points of 800 is 720. But I don't know, I view it as you're sort of climbing this ladder of reaching, once you get those certain number of points, you can't lose them. So that's where the bonuses come in.
You said that before we leave, like you'll tell us what we made.
Yes,
like,
I
full
will.
technique or whatever. So like, will that tell us the letter grade or like the points so that like we
It's
can go
just,
and,
the letter grade's sort of irrelevant at this point.
Mhm.
You could calculate a letter grade based on the total number of points, like up to now in the semester, which would be like 40 plus, so 160, like 185 or something. So what's going to happen is I'm going to basically, like, that's what it looks like.
Oh.
So you're going to hold your exam, like, I'm going to take a picture of it, and they'll grade it immediately. If I remember correctly, it's going to show you, it should show you the total number of points.
Okay.
Oh, so it's gonna tell us the total number of points out of 120, not out of 100.
Yes,
Okay.
I believe so.
That's what I was wondering. So
It's so I didn't use this the last semester, so I sort of forget. But again, I'll take a picture, show it to you, and then you'll know.
And that's what the bonus included,
No.
right? No? Okay.
So the bonus goes through the iClicker.
Oh, that's right.
And so I have to tabulate that separately in Excel.
Okay. And you posted one for spring semester, right? Like an Excel spreadsheet for us to calculate? Or am I like making things up in my head?
I don't think I put one in Canvas
Okay.
yet. I will though. It'll be a little bit different from last semester, but it's sort of the same sheet
Okay.
from last semester.
And then one more question. The bonus questions, are they gonna just like be like questions like the test or?
They're, I mean, sort of what you see in class. So some of them are basically just pulled from the ACS study guide. Some of them you probably already did before in class. So I mean, again, it's hard to find like new questions unless I sit down and write them, which is like, that takes time. And so we have a couple more minutes if there's one last question.
I'm so confused about the top part.
About this one?
So if you were to set it up like these, would you have, like for the Grignard, would it just show everything but the hydrogen? Or, I mean, but for the Grignard, would it just show the hydrogen or?
Yeah, so
Or just like a one bond?
so it wouldn't necessarily be a Grignard. It would be like sodium borohydride or lithium aluminum hydride.
Oh, okay, yeah, that makes more sense. That's
And then this one would be a ketone.
Like sodium borohydride can't reduce like an acid, right? It has to be lithium.
Yes.
Just trying to make sure.
So for oxygen nucleophiles, it was the Williamson ether synthesis. For nitrogen nucleophiles, it's the Gabriel amine synthesis. And so really what that involves is potassium thialimide. So that's that reagent. And it's a source of nitrogen. The nitrogen is protected by these amide type bonds, and there's two amides linked to a nitrogen. It's called an imide, so the A changes to I. And then say we were treating it with two bromobutane. And then for solvent, maybe we have DMF. So this is an SN2 reaction. So we lose potassium bromide. So we're forming a nitrogen-carbon bond. So that gets the nitrogen into the molecule. So it's still, the functional group is still called an imide. So that's IMIDE. And at this point, what you have to do is remove it. So either with acid. So that's going to free up the nitrogen. So this other thing is just the byproduct that you get from it. So that gets you your primary amine, or yeah, your primary amine.
So once you get that like imide, or whatever, you're like adding guess that's where I'm like confused.
So what, yeah, I think probably why you're confused is because I haven't shown the mechanism of how this gets removed. And again, that mechanism comes in like the next module.
Okay.
So, yeah, you're basically removing those bonds, and the nitrogen is getting hydrogens.
So with all three of the types of synthesis of amines, do you know which one to use based on the outcome or like the product that you want, or is it based off of the starting material?
It would be the product you're looking for.
Okay.
So the Gabriel amine and the azide just install nitrogen. But when you have potassium cyanide, it's giving you carbon and nitrogen. So you have to look at your product to see if there's an extra carbon in there.
And those are all gonna give primary amines, right?
They all give primary amines.